section 1.2 of the science section of the Academic Decathlon Resource Guide. To start, we're going to be beginning with scientific notation. Basically, scientific notation is a way to abbreviate really big or really small numbers. For example, we have the mass of the sun given shown right here. I personally can't pronounce this number. What I can pronounce is 2 times 10 to the 30th power, and these two expressions are equivalent. Just one is written way easier and more digestible, and this is known as scientific notation. To use scientific notations, you just count the number of zeros right after the first digit. So if you count the number of zeros right after the 2, there should be 30 zeros. Now, we can also use scientific notation for very small numbers. For example, we have the mass of a single proton, and it's this really, really small number right here. And it can be further simplified to 1 times 10 to the negative 27th power. Negative exponents mean you're dividing by 10 rather than multiplying. So on the previous slide, we had it be a positive number, meaning that we're multiplying by 10. And on this slide, we're dividing by 10 because it's a negative exponent. For example, zero point 0.1 is 10 to the negative 1 power, and 0.01 is 10 to the negative 2 power. And on the image on the right, we can write our scientific notation by counting the amount of digits right after our decimal. So right here, this is our decimal point. We're going to count the number of digits. So 1, 2, 3, 4, 5. So we have 5.14 times 10 to the negative 5 power. And that's how you use scientific notation. And on this slide, I recommend you to memorize this table. Uh, the competition itself might ask really specific questions, so this is really helpful to memorize. Um, just again, scientific notation just makes converting metric units easier because the metric system is all about multiplying and dividing by 10. For example, 1 kilogram is 1,000 grams. 1 kilogram is also equal to 10 to the third power grams, and 1 gram is also equal to 10 to the negative 3 kilograms. And on the side right here, I have written down uh, all these prefixes that you might want to know. So kilo is 1,000, mega is a million, centi is 100, milli is 1,000, micro is a millionth, and nano is a billion. All right here, by the way. The weight of an electron. So there are four fundamental forces in the universe. Uh, one of the fundamental forces is the force of electricity that attracts and repels charged particles. So this is electricity right here. And the other two fundamental forces happens to be in the nucleus. It's the strong and weak nuclear forces. Strong nuclear forces keep both protons and neutrons within the nucleus, while weak nuclear forces transform particles into other particles and is involved in radioactive decay. And the last fundamental force is gravity. And gravity pulls mass towards another mass. The force of gravity depends on three variables: the masses of the two objects and their distance apart. And the equation for gravitational force is force gravity is equal to gravitational constant times m1 m2 over r squared. And I'll be going over these variables in the next slide. When two variables are directly proportional, changing one will change the other in the same way. So, for example, force gravity is directly proportional to m1 and m2. And so basically, this is saying that an increase in m1 will lead to an increase in Fg. So an increase in mass will lead to an increase in force of gravity. If you double the distance, the force is not one half as strong, but rather one half squared as strong, or one fourth. As you see, r stands for distance, so this is known as inverse square law, where the distance is squared and it's in the denominator. So r is squared and it's in the denominator. Because of this, force of gravity is much more sensitive to changes in distance than changes in mass. This is because value being squared is makes it more sensitive than a number that is not squared, which is our two masses right here. And then there's also G, which is known as our gravitational constant. Compared to the other masses, G is effectively zero, and the our value for G is 6.67 times 10 to the negative 11th power newtons meter squared per kilogram squared. And for reference, the mass of the Earth is 6 times 10 to the 24th kilograms. And since the mass of the Earth is so huge, we tend to notice only Earth's gravity and not any other object significantly smaller. And then we'll move on to the masses of a proton and electron. The mass of a proton is 1.7 times 10 to the negative 27th kilograms, while the mass of an electron is 9.1 times 10 to the negative 31 kilograms. Notice how a proton has more mass. Gravity is meaningless at the scale, so we'll move on to the next fundamental force, which is gravity. We'll move on to Coulomb's law. The following equation on the right is Coulomb's law. Force electricity is equal to Coulomb's constant Q1 times Q2 over R squared. The equation was discovered by Charles Coulomb in 1785. Coulomb used a torsion balance in which a charged rod is suspended by a string and can be twisted by the slight electric forces created by the charge. Q1 and Q2 represent the amount of charge on the two objects, and it's measured in coulombs. R again is their distance apart, and K is known as the Coulomb constant. Since coulombs are scaled based on human devices, one coulomb is huge compared to the charge of a proton or electron. So the image on the right shows that one coulomb is about 6.24 quintillion electrons. Um, the charge of both particles, meaning for a proton and electron, is plus or minus 1.7 times 10 to negative 19 power coulombs, where protons are the positive and electrons are the negative. Another glance at Coulomb's law shows that it is very similar to our force of gravity equation. Remember, force of gravity is equal to gravitational constant m1 times m2 over r squared. You notice how they have both r squared? This makes it inverse square law, where distance is squared and it's in the denominator. So twice as much distance results in one-fourth as much electric force. However, we can also see that there are some differences. Electric force can be attractive or repulsive, while gravity is only attractive. Another difference is the constant K. K is equal to 8.99 times 10 to the ninth power newtons meter squared per coulomb squared. K is a very large number compared to G. In the case of two electrons, the electrical forces beat out gravitational force. So the reason why we don't see electric force as much as gravitational force is that most atoms are electrically neutral, meaning that most atoms have an equal amount of protons and electrons. Thus, the atom's net charge is zero. Electric fields. In physics, the concept of a field is where we assign a numerical value to every point in space due to some phenomenon. There are two commonly used types of fields. We have scalar and vector. So a vector refers to a quantity that has both magnitude and direction, like velocity. So a car moving west at 20 meters per hour versus a car moving north at 20 miles per hour. Sorry. So although they have the same speed, they have different velocities because one car is moving west while the other is moving north. And then a scalar quantity refers to only having magnitude. For example, we have speed and mass. Mass is constant regardless of the direction. An example of a scalar field is temperature in a room. You can calculate the overall average, but different parts of the room have different temperatures. Every point in the room has different temperature associated with it. And an example of a vector field is the wind over the surface of the earth. The wind blowing at different speeds, it has different directions, so every point has a different vector describing the wind. Gravity is also a vector field. The gravitational field always points toward the center of the Earth. We can rewrite our force of gravity equation to force of gravity equals to mass times gravitational acceleration due to gravity, which follows Newton's second law. Remember that Newton's second law was equal to force is equal to mass times acceleration. This equation up here is also weight. M is the mass of the object, and g is acceleration due to gravity, where g is approximately 9.8 newtons per kilogram, or also meters per second squared since its acceleration. The further away from the ground, g decreases. Most satellites in orbit have 90% of g, while the moon has less than 1%. A similar equation can be written for the electric force equation with electric force is equal to Q times E, where Q is the charge of the object and E is the electric field, measured in newtons per coulomb. Since protons have a positive charge, the electric force that they feel will point in the same direction as E, and the opposite for electrons. So a single proton will always have an electric field around it that points away from it. So if we look at this image right here, this is an image of a proton, and the electric field always points away from, always. The equation for the strength of a proton's electric field is given as electric field is equal to Coulomb's constant times Q over R squared. This is the same for an electron. This is exactly like Coulomb's law, but with less one Q. So if we add another Q right here, it'd be the exact same thing as Coulomb's law. Now with a single electron, the electric field always points inwards. So reminder that a proton points outwards while an electron points inwards. If we place two protons next to each other, they will be pushed away from each other due to the electric fields pointing outward. On the other hand, a proton and electron will attract due to their electric fields differences. In the laboratory, most of the time we mainly calculate the electric fields of large objects rather than individual particles. It is easier because we can add up electric fields for multiple objects. For example, if we have two protons near each other, they will create their own electric field. From far away, the electric field may look doubled of the charge of a proton. However, if we zoom closer in directly between the protons, with one pointing to the right and the other pointing to the left, the electric field is zero. So right between these two protons here, the electric field is zero. Now let's see what happens when it's both a proton and electron. So if we have a proton and electron, the electric field will be zero far away. So in contrast, the electric field is zero for a proton and proton directly in the middle, while the electric field is zero between a proton and electron far away. So like right here, maybe from those two particles. And directly between a proton and electron, so right here, the electric field is amplified as both the electric fields point to the right. So we can see that since a proton's electric field points outwards, and a electron's electric field points inwards, they both go to the right, and thus the electric field is amplified. Now, if we add a third charge around the proton and electron, its trajectory will follow the field lines, while a negative charge will go in the opposite direction. This is known as electric dipole. Remember that di means two, so we have two sides, one positive, one negative. Certain molecules can have a positive and negative side, which creates electric fields that affect nearby charges. For simple geometric shapes, we do not necessarily need to calculate every single particle and its charge. That's just too tedious and a lot of work. Instead, we can use symmetry to avoid much calculation, which brings us to our next section, symmetry and Gauss's law. So to first start, let's imagine two tugboats on the opposite sides of a large steamship. So one is pulling this way, the other is pulling this way. They have equal strength but are traveling in opposite directions. So what's going to happen? Well, since they have equal strength, but are traveling in opposite directions, we can say that the steamship is going to remain stationary because it's getting tugged equally from both sides. Now we can apply the same thing to charges. So if we had two positively charged particles stuck in place and a proton is placed directly between them, what will happen? Remember that a proton points outwards and this proton also points outwards. These forces cancel out and we're left with this proton being stationary. So the proton will be equally repelled by both spheres. Remember that the electric field for a positively charged particle points outwards. Now, if you nudge the proton a little forward, like this, like so, it will start moving forward. It still has the same distance from the spheres, but it now has a forward component. Since there is nothing to cancel out the forward component, the proton will move forward. Both forward components add up. So we can see right here that uh, the electric force forward component adds up and causes our proton to move forward. Next, we can move on to Gauss's law, which offers a technique to figure out what the electric field looks like for extended objects. The equation for Gauss's law is phi is equal to q over epsilon, where phi is the electric flux and epsilon is the permittivity of free space. So again, this Greek letter right here is epsilon, and it's known as the permittivity of free space, and it's directly related to Coulomb's constant. Right now, in this section, we will not dive into what it means, however, it will be important later. Just know the equation for the permittivity of free space, and it's equal to 1 over 4 pi k, where k is our Coulomb's constant. Okay, and then Q represents the total charge contained within our Gaussian surface. So this is our Q. And then we have phi right here. It's known as our electric field flux. The electric field flux is a scalar quantity where the flux of something is the amount of it that passes through a given area. The electric field flux depends on the strength of the electric field and how the area is oriented relative to the field. So numerically, the electric field flux is the strength of the electric field E multiplied by the surface area A. So we can also write our electric field flux as phi is equal to E times A. And remember our equation from the beginning that this electric field flux is equal to Q over epsilon. So these two expressions are equivalent, and this will be important later. Now we can think of flux as rain falling into a bucket. So if rain is upright, lots of rain gets in. If the bucket is sideways, barely rain enters. Now if the bucket has no bottom, rain flows straight through and cancels out, and thus the net flux is zero. Now, if we take a flat sheet of charge in our scenario, and we just want to take a look at the electric field in the middle, so right here, we can put our Gaussian surface in the middle of it. And basically what a Gaussian surface is, it's just a tool of analysis, and it's an imaginary closed surface to calculate electric fields. Again, it's imaginary. For a Gaussian surface, we want a symmetric shape, and where calculating area is easy. Since we have a flat sheet right here, we want to use a cylinder. A cylinder has three surfaces. We have the top, the bottom, and the side. If our cylinder is oriented so the top of the cylinder pokes out, like so, through the sheet of charge, we can calculate the electric field. Since the electric field is completely vertical, meaning it's only up and down, none of the flux goes to the side. So there's nothing going on right here. The top and bottom have an equal flux, meaning they have the same strength because they are equally distanced from each other. Since there is a flux coming from the top and bottom of the cylinder, we can calculate the electric field flux with the equation phi is equal to E times A. Remember from the previous slides, where E represents the electric field strength and A being our surface area. Since we have a top and bottom, we also have two surface areas to calculate. So remember, A is our surface area, and since we have a cylinder, we have one right here and our second one right here. Thus, we have two surface areas. So we can set our two equivalent expressions together. Remember that EA is equal to Q over epsilon. So we have 2EA over Q over epsilon. Since Q is the total charge on the surface, we want to rewrite Q where it contains a portion. We want to portion it our Gaussian surface. To do that, we can rewrite Q as sigma times A, where sigma is our surface charge density, which is the amount of charge per area, and A, again, represents our surface area. Like water's density, charge density is also constant. Now, let's solve for E. To do that, let's isolate E. So remember from our previous slides, we had 2EA equal to, and then we remember that we wrote Q as sigma times A, so sigma times A over epsilon. And to isolate E, we can cancel out A on both sides, um, and we can also multiply both sides by 1/2 to cancel out the 2. So we're going to be left with E electric field is equal to sigma over 2 epsilon. And note that the electric field depends on density and the charge. Remember, sigma is our surface charge density, and our constant is the epsilon right here, or permittivity of free space. And now that's the end of this section, but I know that this video is long, so I'm going to provide a little review for you guys. So to first start, scientific notation is a way to write really big or really small numbers. And we use it to abbreviate really big numbers using forms of 10. We have four fundamental forces in nature. We have strong, weak nuclear force, gravitational force, and electric force. The equation for gravitational force is force of gravity is equal to gravitational constant m1 times m2 over r squared. Inverse square law describes an equation where a number is squared and it's in the denominator. G is the gravitational constant and its value is 6.67 times 10 to the negative 11 newtons meter squared per kilogram squared. Coulomb's law measures electric force and is equal to Coulomb's constant Q1 times Q2 over r squared. Coulomb's constant is K is 8.99 times 10 to the 9th power newtons meters squared per coulomb squared. We have two types of electric fields. We have scalar and vector. Scalar has no direction, while a vector has both direction and magnitude. We can write our gravitational and electric force equations as force gravity equals to mass times gravitational acceleration, and electric force is equal to Q times electric field, respectively. The electric field for a proton points outwards while an electron points inwards. The strength of a proton's electric field is given as E is equal to Coulomb's constant times Q over r squared. If we have multiple electric fields, we can add them. Directly between two protons, the electric field is 0. Directly between a proton and electron, the electric field is reinforced/amplified. We can use symmetry to avoid tedious calculations. If it's equal strength on opposite sides, the net strength is 0. The equation for Gauss's law is phi is equal to Q over epsilon. The variable epsilon is known as the permittivity of free space, where it is equal to 1 over 4 pi k. The electric field flux depends on the electric field and how the area is oriented to the field. So phi is equal to E times A. Our total charge Q is equal to our surface charge density times our surface area. So Q is equal to sigma times A. And this is the last slide of this video, and I just wanted to go over the variables because I know the variables are really confusing. When I first started studying for this section. So remember that G is our gravitational constant, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. K is our Coulomb's constant. G is our acceleration due to gravity, and it's 9.8 meters per second squared. Q is our electric charge. The symbol right here is called phi. It's our electric field flux. The symbol right here is sigma, which you guys are. Uh, it's our surface charge density. The symbol right here is epsilon. It's the permittivity of free space, and it's 1 over 4 pi k. And then E is our electric field. And then these are some numbers that you might have to memorize. So the mass of a proton is 1.7 times 10 to the negative 27 kilograms. The mass of an electron is 9.1 times 10 to the negative 31 kilograms. And the charge of both particles for both protons and electrons is plus or minus 1.7 times 10 to the negative 19 coulombs, where protons is positive and electrons is negative. And this is the end for this section. I know this video was quite long, um, but yeah, thank you for watching this video. I will see you in the next video. Thank you for watching.